All right, let's fix the hair. Okay, good morning, gang. Sorry, I just gotta first look at my hair here because I didn't look in the mirror this morning and realize I'm looking a little bit like a fool. So I'm gonna take a second to fix that, and then we're gonna start talking about volumes. Oh. Okay. Looks like folks are getting in. That is good. Just gonna power it up. Cam is whizzing and buzzing. QCam all connected. All right, good morning, everybody. Here we are, the start of the second week. I do want to say a thing or two before we get started. So I've noticed that not everybody is using their real name when they sign into Zoom. That's not the end of the world, and I understand if you don't like putting your actual name into random things online, but this isn't really a random thing, and I do use the Zoom logs to take attendance, and although there's no attendance component to the grade in this class, I do need to report your attendance for financial aid purposes. So please use your real name. Or at least a discernible pseudonym. I posted a little announcement about this over the weekend when I went in and updated all of my attendance things. Like I published your guys' first attendance record last Monday. And then I think I did another one Friday, and then I did one more on Sunday, but I believe there are still a few people who are missing, and I think it's possible that a few of those people have been here. I'm just not sure who they are because it says, iPhone instead of, Sammy's iPhone, or it says, just a phone number, I think in one case. I don't remember whether that was your class or not, but do me a favor and use like first name, first initial, last name, or something from which I can discern your real name as your username here in Zoom. That way I can get you marked as having attended. You can see whether you've been marked as attended or not in eSanta Fe. And if you've been marked attended, don't worry about it. But if you haven't, please make sure you clear that up with me one way or the other. And besides that, the only thing we're going to do today is start learning about volumes. There's two sections. 6.2, this is by slicing discs, washers. Sounds like three different methods, but it's really just one method. So that's section 6.2. And section 6.3, which is volumes by what is called cylindrical shells. So I think we're definitely not going to cover both sections today. Today we're going to talk about 6.2. And then Wednesday, I'll do some more 6.2 examples and finish up Wednesday with a little bit of 6.3. And then Friday, we'll do all 6.3 examples, maybe a few from 6.2. This section has some challenges that come from places you might not expect. So it's got some geometry, which is to be expected because we're talking about volume, which is a geometric thing. But if you're not very good at drawing 3D images, you might find these two sections a little bit challenging. I'm not perfect at drawing 3D images. God knows I'm not. I'll do my best through this to give you workable, presentable images to work with. And you want to make sure you just take your time and draw the pictures. This is another one of those instances where WebAssign cannot force your hand, cannot make you draw things. But if you don't, if you just try to work from formulas or whatnot, it's going to bite you in the ass. So I would encourage you, draw the pictures, draw them large, draw them patiently, and try to really understand what's going on. You won't find this too hard. A very brief overview of how this will work. We will find a small segment of volume which I'll call dV. That we will integrate to recover or to find the whole volume V. So for all of these problems, all of the three kind of little tricks from 6.2 and everywhere in 6.3, we'll be trying to find the volume of some large solid. And in each one of those, we're going to take some little portion of that solid, and maybe it'll look different. The little portion might have a different shape in each one of the different tricks. But that little tiny little solid that will be a part of the whole solid will have a tiny little volume. That tiny little volume I call dV. And then we're going to integrate dV to get the whole of the volume V. So let me begin with a really trivial example, sometimes called a motivating example. By slicing. So I think probably everybody knows the formula to find the volume of a right circular cylinder. That is like a soup can. You take the area of the cross section, the circle, and you multiply it by the length. But imagine I had that soup can laying on its side here. And I didn't know the formula for the volume of a right circular cylinder, which is what this is. Circular because the cross sections are circles. Right because this angle here, the angle between the length and the base, is a right angle. So called a right circular cylinder. If I wanted to find the volume of this thing, I would want to do two things. First, I need to introduce some coordinates. Right now, I don't have any variables, don't have any coordinate system. So I'm going to pretend like this cylinder is sitting on like a barbecue spit. I'll call that the x-axis. And then I imagine taking a little slice the slice has a thickness, dx, and I'm imagining it taking place in here at an arbitrary x value, which I'll just call x. So along the x-axis, I pick a number, I call that x, and I take a slice there. What I want to do is find the volume of this little slice. That's the little volume I will call dV. So I take a slice perpendicular to the x-axis with thickness dx. The volume of this little slice, I need to give you some dimensions for this thing, so we can say that this is a cylinder of radius r and length L. So if I look just at that slice now, it still has thickness dx there, and the radius here is r. Maybe I should take this off here. The radius here is r. So the volume of this little slice, dV, is this area times this little thickness. That's pi r squared dx. So if this right here is x equals 0, and we said the total length of the thing is L, so this would be x equals L, then the way I would find the volume of the whole cylinder is by integrating from x equals 0 to x equals L, this expression. So this implies that V would be the integral from 0 to L of dV, which is pi r squared dx. And when you integrate pi r squared dx, these are both constants, you get pi r squared times x evaluated from 0 to L. If you plug in 0 for x, this whole thing becomes 0. If you plug in L for x, you get pi r squared times L. And that is the formula for a right circular cylinder's volume. It's the cross-sectional area times the length. And as long as you have a constant cross-section, that's the fun thing to notice here. If you were to move this piece around, if you were to bring it back here or over here, the dV slice here has the same volume, no matter where you take the slice. So this is what I call a boring or trivial or motivating example to kind of help you see in the simplest possible case what it is that we're doing. So I want to pause here for a second and see if there's any questions about the mechanics here. So never mind that this slice isn't special, that its volume was easy to find. Do you understand the idea of adding up the volume of all these little slices using an integral? Because that's really what's going on here. This little dV slice is now your little Riemann rectangle. That's the idea. Instead of having a Riemann rectangle, you have now a little Riemann slice. And so you take the slice over here and you add it to the next one, and you add it to the next one, you add it to the next one, and you want to do that in a continuous way. Infinitely many of these very, very little slices. Well, that's what an integral does. And we talked about that last week when we talked about finding average values, how integrals are really a nice way of adding up a bunch of things over a continuous range. How do we feel about this? We feel kind of okay, mostly okay, a little bit weird. What are we thinking? I know it's early. I would love to hear anything that you're thinking, just so I can know that we're here and we're paying attention. Any thoughts at all on this? It makes sense. It doesn't make sense. What the fuck are you doing? Why am I alive? You know, anything. Yeah, thumbs up from Todd. That's good. That's about as much as I guess I can demand at 8 a.m. So let me try to ratchet up the difficulty a tiny bit by looking at a pyramid instead of a cylinder. Eventually, we're going to be looking at very, very strange shapes here. So let's find the volume of a pyramid whose square base has side lengths L and has height H. I do see a question in chat there, so before I proceed, let me take a look at that. Still pondering. Okay, that's okay. So see if this example doesn't help the pondering. Again, I'm going to do my best to draw this. So we've got a pyramid whose base is a square. Okay, well, here's a square just kind of chilling. And he's got a height, h. So that should look something like this, right? And the height would be the thing that I drop straight down through the middle here and meets the base at 90 degrees. That's h. And this length here is the same as all the other side lengths. Those are all L. So I want to find the volume of this solid. Similar to the right circular cylinder, I can take a slice. So I imagine bringing, you know, a white hot plane through here and slicing. I would like to try and find the volume of the little slice that I cut out and then see how that changes depending on the height, and then integrate that slice's cross-sectional area times its thickness. To make it more similar to the problem we were just looking at, I'm going to turn the pyramid on its side and poke it through with an axis like a barbecue spit, just like we did. So here's the pyramid lying on its side. Again, I'll do my best to draw it in 3D. Maybe I'll have my height poke out first. That way I have something to aim for with these. All right, so here's my pyramid sitting on its side. And this guy, I'm going to allow to poke straight through. This is my x-axis. Yes. So we would use the height to determine the bounds. And in this case, we're going like left to right because of how I've drawn the picture. So down here would be x equals 0, where we poke through the floor. And up here would be x equals h. And what I want to imagine doing is taking a little slice and trying to find the volume of that little slice. So the thickness of the slice would be dx, and the volume of my little slice I'll call dv. Here though, the volume of this little slice, that is going to change. If I'm taking, so I imagine here I'm taking the slice at a point I'll call x. If x was all the way up here at h, then this cross section, this slice would have volume 0. And if it was all the way back here at the base at x equals 0, the volume of the slice would be L squared, because that's this length and this length, times dx. In order to find the formula that tells you what the volume of this slice is at any x value between 0 and h, I think it will be instructive to look just straight on at the side. So rather than trying to draw this in 3D, I'll look straight on the side. So looking side on. This right here is x equals 0. This right here is x equals h. And if I choose to take my slice at some x value in between, like right here, we're going to make use of some triangle rules, right? So if you look at the little triangle here, he's similar to the big triangle here. So the little triangle here, first let's make some observations about my dv slice. Let me come back to this step. So my dv slice looks like this. Because the base of the pyramid is square, the face of this slice is square. The thickness is still dx. But I need to find the area of this little cross section. So that's going to be this length times this length. Can you guys see that? This length here is this length here, these guys. I'm just taking this slice out of this picture. So this length here is this length here. This length here is this length here. Since the base of the pyramid is a square, every cross section is also a square. So really, I just need to find this length here, or any one of those lengths. It doesn't matter which one you're thinking about. I guess I shouldn't call it L because we've called something else L. But these guys, I need these guys. Maybe use, whatever I'll use. I don't want to change things too much. What should we call this? Lambda? Greek letters scare people. Let me go back and retcon this into a capital L so I can use little l's for those, okay? Big L for the overall base length and little l's for the little lengths. That makes sense, right? Okay. So the base of the pyramid, I'm gonna call that big L so I can use little l's here. I think it's clear that if we're slicing at x equals 0, then little l is equal to big L. And if we're slicing all the way out here at x equals h, little l is 0. But if I'm slicing at some x value in between, like here, then I need to know what's the relationship between x and this side length. So in other words, in this picture, here is little l. Here is little l. And little l clearly changes with x. So dV, the volume of this little solid, is L times dx, right? This is just a little rectangular prism. So it's L squared dx. But we need to find little l. Little l is actually a function of x. So little l is a function of x. It changes depending on where you slice. And the place where I'm slicing, that's what we're calling x. So this x right here indicates where along this axis we are taking the slice. That slice is a little square prism. So its volume will be its side lengths times its thickness, length times width times height or whatever. Since two of those are equal to each other, what we're calling little l, that's the same as L squared times this width, this thickness, which is dx. And now down here, I'm looking straight on the side so I can try to figure out how L changes with x. We'll be integrating from 0 to h, but we're not done yet. We're not ready to do that yet because I don't know how this L squared changes as x changes. So what we need to do is come back here. Right? I know that this whole triangle, this is one side of the base, so that has length capital L. And I know that the little triangle here is similar to the big triangle. So this little triangle has the same ratio of side lengths as this big triangle. So what does that tell us? Well, if this side length here is little l, is the thing I'm after, then I can set up the relationship big L over h by similar triangles. Big L over h is equal to little l divided by, what is this distance? So here's big L over h. That must be equal to little l over this distance. And that distance is h minus x. Yeah, good. So now I'll solve this for little l. I'll plug that in here, and then I'll integrate from 0 to h. So this implies I'll multiply both sides by h minus x. That big L over little h times h minus x is equal to little l. So I'm just multiplying both sides here by this h minus x to get little l alone. Therefore, dv, which is little l squared times dx, is L over h times h minus x all squared times dx. And therefore, the total volume V, which is the integral from 0 to h of dV, is the integral from 0 to h of L over h times h minus x all squared dx. Let's not get these confused. Okay, so this is considerably more complicated than the last question. I'd like to take a second and make sure we're all okay with where everything came from, especially that similar triangle argument. I know that can be hard to spot. What are we thinking? So I'm always taking slices of differential thickness. That's a good question. How do I decide what dx is? So once I've chosen my axis, once I've given us some coordinates, remember that was our first step last time also, was to like skewer the soup can with a barbecue spit. Once I've chosen my axis along which I want to integrate, the thickness of the slice will always be a differential element of that variable's thickness. So since I poked it through with an axis and I labeled that axis as x, a little thickness along that axis is automatically going to be dx. Dx isn't a known quantity, it's just a little differential thickness. So in other words, in this picture here, the dx would be like this thickness. Here I'm looking side on at my pyramid, so this little blue highlighted area, this is like looking side on at my dv. That's looking side on at this object, stuck inside our pyramid. Does that answer your question? Okay, cool. What else are we thinking? Anything else bugging us right now? Yes, we do. Yes, we do need to simplify this before we can integrate. The variable I'm integrating with respect to is x. So really, this is the only piece that the integral cares about. Everything else is constant. So I need to square this. I'll need to FOIL this out. So let's go ahead and do that. I'll continue the integral down here. That's the integral from 0 to h. This will be capital L squared over little h squared times h minus x squared dx. So because this L over h is multiplying the h minus x, I can give the square to this chunk and to this chunk separately. When I square the capital L over h, I get L squared over h squared. And when I square this guy, I'm going to have to FOIL. But I'll do those in two separate steps because I want to bring this guy outside the integral. Capital L and little h are both constants, so I can pop that out. So I'll have L squared over h squared times the integral from 0 to h of, and now I need to square out h minus x. So that'll be h squared minus 2hx plus x squared. And the integral is still being done dx. And now we're ready to integrate. So I'm going to take this down here. The capital L squared over h squared will still be there. And now for the antiderivatives, h squared integrated dx is h squared x. Minus 2hx, that will integrate to minus hx squared. Because when you integrate the x, you'll get x squared over 2, and the 2's will cancel. And then when we integrate the x squared, we'll get 1/3 x cubed. And all of this is to be evaluated from 0 to h. So each one of those antiderivatives is fairly easy. It's a power rule thing. Just got to be a little careful about what the variable is. And what you see is when I plug in x equals 0, this is 0, this is 0, and this is 0. So the lower bound doesn't contribute anything. It's all going to come from plugging in this upper bound. So my L squared over h squared up front, still hanging on for the ride. When I plug in h, I'll have h squared times h, that's h cubed, minus h times h squared, so minus h cubed, okay, plus 1/3 h cubed. And like I said, when we plug in 0, when we plug in the lower bound, everything is 0, so we don't need to worry about that. These guys cancel, so we'll just have this surviving times this. So that's L squared over h squared times 1/3 h cubed. The h cubed and the h squareds will cancel, and we'll get 1/3 L squared times h. And if you know the formula for the volume of a cone, this looks somewhat similar. 1/3 times the area of the base times the height. The hard part here is definitely all this setup work. So I'll give a second for those who are writing down here, and then I want to return to the setup and make sure we're all comfy with where that's coming from. And then we're going to talk about the disk/washer method, which is very similar, same thing technically. Any questions on the antiderivative step here? Or on the evaluation step? Okay, good. So then let me come back up here. I think this is all the hard work. So questions, let's start here. Why this slice looks like this, why it has this volume, or why this little L is a function of X. Why do we have to take time to figure that out? Can we all see what would happen as I move this slice towards the base or towards the tip here? As I move this slice towards the tip, it's getting smaller. And as I move this slice towards the base, it's getting bigger, because the cross sections are getting bigger and smaller as we move in those respective directions. So in order to figure out this guy, which is what I have and what I need to integrate, I need to find a formula for L, because L is not, little l here is not constant. When x is way up here, little l is quite small. When x is back here, little l is quite large. And that's where looking side on became really helpful. So this guy is my little l. This thickness here is my dx thickness. And I'm able to use that similar triangle argument that says ratios of two similar triangles' side lengths have to be the same. So since the little triangle in here is similar to the large triangle out here, if I take his ratio of side lengths, say this base to this height, big L to little h, this base over this height, that's a ratio of side lengths. That should be the same as this base to this height. This base is x. I'm sorry, this base is not x, this base is L. It's a slice being taken at x, but the length here is at little l, the thing I want. And this distance, since this is x equals h, and this is x equals x, this distance is h minus x. So big L over h, this base over this height, has to be equal to this base over this height, which is little l over h minus x. Then we solved that relation for little l, and we plugged that in to our dv. And then from there, it was all gravy. Yeah, just a little bit of basic algebra and power rule integrals. So this is what's called the method of slicing. And we use the method of slicing when we don't have a lot of rotational symmetry. So here, this object isn't symmetric there's no axis about which you can rotate this thing so that it always stays symmetric. Most of the volume problems you're going to see, though, will be problems where we have a lot of rotational symmetry. So last call for questions on this example here where we use the method of slicing. What do I do if you can't draw pyramids to save your life? Try your best. For each of these, just try your best to draw. I find that the bigger I draw the pictures, the more room I have for mistake. Rulers might be helpful, yeah, a straight edge of some sort. But mostly, just be patient. Don't rush your drawings, take your time. I'm gonna change gears just slightly. It's only gonna seem like a second here where we change gears, because I wanna talk about solids of revolution. So pyramid is a solid, but you can't think of the pyramid as coming from revolving a region in the plane about a particular axis, because it doesn't have full rotational symmetry. I think I mentioned this briefly at the end of class last time. If I take an upper semicircle, I take this region, and I rotate it like this. Again, imagine it's like a barbecue spit. If I could pick this guy up and spin it, then it would sweep out a solid as I do that. It would sweep out a little sphere. Or if I took a full circular region over here, and I spin it like this, so here I would get a little sphere. The region was an upper semicircle. we rotated about the x-axis, and the resulting solid was a sphere. Here, if I take the region that is a whole circle, right, so I'll draw the solid down here. Sphere, not too hard to draw. And I rotate it about the y-axis, you can imagine, you know, I can spin this, then it's going to come flying out of the page and then go back into the page. It's going to come like this. And the result there is going to be what's called a torus. So if I take a circle that's centered along the positive x-axis and I rotate about the y-axis, then the resulting solid is going to look like a donut. In math land, we call that a torus. I'll do my best to draw for you a torus here. I haven't done this in so long. Let's see. It's going to come out shitty, isn't it? Fuck. How do you do this? Wait. I used to be really good at drawing these. You get this, a torus. Right. I have to remember how I used to draw these. I had a trick that I just can't seem to remember at the moment. Something like that. Yeah, forgive my horrible art. Anyway, so if you rotate this about this axis, then this circle is going to come out of the page. It's going to spin around like that, and you'll get this donut shape. If you rotated this guy about the horizontal axis, you'll get a sphere. Solids like these are called solids of revolution. Solids which arise from rotating a region in the plane about a line are called solids of revolution. And most of the solids that we're going to work with are solids of revolution. And we have some special tricks for how to do the slicing method with those. Oh, that's right. Yeah, okay. I just remembered how to sketch my torus here. I cheated a little bit. So you do this, you do this, and then you put the whole thing in like a big oval, right? Yeah, there we go. That's a pretty good looking torus. Okay. So these solids that come from rotating a region in the plane are called solids of revolution. And when it comes to solids of revolution, there are some tricks that will help you find the volume without having to go through a pure geometric argument all the time. So the method I'm going to introduce here is called the method of disks and washers. And the way this works is you identify your region. Within that little region, you draw a little Riemann rectangle. And then you imagine just rotating that rectangle. So leave some blank space in your notes here. I'm going to come back and fill in a little formula that you can use. And the formula I'm going to give you is the most general formula that you can really trust. If you go Googling, you'll find other formulas, but they break down in certain problems. And I will be putting problems on your test for which those internet formulas break down. So I encourage you to work just with the formula I'm going to give you here. But I want to discover that formula by playing with an example. So let's find the volume of the solid obtained by rotating the region bounded by y equals x, x equals 0, x equals 2, and y equals 0 about the x-axis. So you need to specify a region, and that's going to come from your area between curves stuff, right? All the sketching that you did there. And then you're going to imagine rotating that region about some line. And the first few examples I'll do will rotate about one of the coordinate axes, but later we'll be rotating about other things as well. Y equals x, well, that's the line through the origin with slope 1. So you want to draw your pictures and draw them nice and big. So there's the line y equals x. X equals 0, that's the y-axis. Y equals 0, that's the x-axis. X equals 2, that's like right here. So this is my region. And I want to rotate that about the x-axis. You can see what you're going to get. The result is going to be a pyramid, not a pyramid, sorry, a cone sitting on its side. The solid here, I'll try to draw it to scale. It's going to look like this. Can we all see that? If you spin this around, the object that it sweeps out as it spins around will be this cone. You could even tell me what the radius is. The radius is whatever this length is. And since this is the line y equals x, this is the point 2, 2. You know that the radius here is 2. So you could use a geometry formula to find this volume if you wanted to. But I want to show you how to set it up as a disk washer problem. Are we all comfortable with this region sweeping out that cone as we rotate about the x-axis? Can everybody kind of see that? Are there any questions about that? Yeah, as long as you can visualize it, that's a good step. Your pictures don't have to be perfect. I am not going to judge you on the quality of your art, I promise. The first step to solving this problem is to draw in a little differential thickness strip. And for this method, the method of disks and washers, we always draw that strip in perpendicular to the axis of rotation. So here the axis of rotation is this horizontal line, the x-axis. So I'm going to draw my strip in perpendicular to that. It's always understood that this strip is at an arbitrary position, x, in my region. And the point up here at the top of my strip, because I'm along y equals x, is going to be x comma x. Because I'm along the graph y equals x. So this point would normally we just call it x comma y, except because I'm on the graph y equals x, y is equal to x. Imagine rotating just the strip. So first you draw the strip. The strip has thickness dx. If I take just this strip and I rotate it about this x-axis, then I'm going to get a little disk. This is my dv. And you can see how this is connected to the slicing method. This disk is what you would get if you sliced this. Does everybody see that? This disk that you get from just rotating this strip is what you would get if you came in here and sliced this cone. So this method that we're learning right now, the method of disks and washers, is equivalent to the slicing method. It's just kind of a shortcut. And while it might not seem like a shortcut right now, I promise you it is. The disk has a radius that I will call r, and a thickness of, in this case, dx, because my strip is a vertical strip, so its thickness is a little horizontal thickness, is an x thickness, or a change in x, right? The thickness of this strip is dx. So the dimensions of a disk are always the same. The volume is going to be pi r squared times dx, the area of the cross section times the thickness. And here, r, we can figure out. The radius of this disk is the length of this strip, or the distance from the end of the strip to the axis of rotation. So this is r. Up here, the y value is equal to x. Down here, the y value is equal to 0. So this distance from the curve to the axis of rotation, or from the end of my strip to the axis of rotation, this height here is x. So dv is pi times r squared, r is x, so that's pi times x squared dx. Therefore, my volume, that's going to be the integral from the smallest x value in my region to the largest x value in my region, so from 0 to 2 of dv. And that's the integral from 0 to 2 of, well, what was dv? It's pi times x squared dx. And this is not a challenging integral. That's pi times the integral from 0 to 2 of x squared dx. That's pi times an antiderivative for x squared is 1/3 x cubed. And I need to evaluate from 0 to 2. And when I plug in 0, I get 0, so I don't need to worry about that. When I plug in 2, 2 cubed is 8, so that's pi times 8/3. And that's my volume. So to use the method of disks and washers, you first sketch the region that you're rotating. Indicate which axis or what line is the axis of rotation. And then you draw a strip extending from the top of your region to the bottom of your region, or extending over the length of your region that is perpendicular to the axis of rotation. The distance from the far end of the strip to the near end of the strip, that's your radius. And then you just rock and roll with this formula. dV is the solid you get just by rotating that strip. It's got a little differential thickness and a radius. It's a disk, that's why we call this the method of disks. I'll show you the washer thing in a minute, it's the same sort of thing. Then you need to go back to your graph here and figure out what distance in that setting is the radius of your disk. Since that disk is coming from rotating just this strip, here the radius has to be the length of the strip. So r is, in this case, equal to x, because the distance from here to here is x, because you're looking along the graph y equals x. You plug that into your formula for dv, and then v is, as always, the integral of dv. In this case, we run from 0, because that's the smallest x value anywhere in my region, to 2, because that's the largest x value anywhere in my region. And from there, we just crunch out the integral. Not too bad, right? So I want to return to this space that you left in your notes here. If you didn't leave space there, just make it now. The method of disks and washers. It all comes down to your formula for dV. dV here is pi times, I'm actually going to use two symbols, capital R squared minus little r squared times, I'm going to say dt, where capital R and little r, cap R is the distance from the further end of the strip to the axis of rotation. And little r is the distance from the nearer end of the strip to the axis of rotation. And the most important thing that you remember for this method is that the strip is drawn perpendicular to the axis of rotation. Okay, so that's the method here. I'm using the symbol dt rather than dx because sometimes these integrals will be dy integrals, sometimes they'll be dx integrals, and I don't want the formula to pin you down to one or the other. You've got two radii here, and that's accounting for the washer part of the disk washer method. I'll show you an example like that in just a second. In the example we just did, there was only one radius because there was no gap between my strip and the axis of rotation. So to give you a feel for the level of complexity these usually have, I want to grab an example from your textbook. Here's them talking about slicing. They've got some very nice pictures in here, right? So you've got your solid, you take a slice, and then you're able to find the volume of this little differential thickness slice, and then you integrate that. They do a few more examples like this. These are all well and good, but we need to find one where we have a washer. Yeah, okay. So because my art is not perfect, I want you guys to take a look at the picture as it is here. So I'm going to go ahead and write the example down. We want to find the solid. Find the volume of the solid generated by rotating the region bounded by y equals x and y equals x squared about the x axis. So I'll draw my picture and I'll draw it nice and large. Here's y equals x squared. And here is y equals x. I'm rotating about the x-axis. So I'm going to come in here to my region, which is this region, and I'm going to draw in a strip that is perpendicular to the axis of rotation. So I'm going to draw in a strip that looks like this. With the understanding that this is taking place at the x value here, just x, an arbitrary x value. And then I imagine rotating just that strip. If I were to rotate just this strip about the x-axis, it's going to come out the page, go back into the page. I'll get something that looks like this. A washer, right? Imagine this strip being spun around like this. I spin it around like this, the strip will come out of the page and then back down into the page. There will be this little gap in here. This little gap is what we call little r. And the big radius, the radius from the center of this thing to the edge overall, we call that big R. the thickness here. This is still a dx thickness. And to find the volume of this little differential solid, I imagine that it's a big disk with the little disk punched out. So dV here is pi times capital R squared dx minus pi times little r squared dx. And you can factor the pi and the dx. You get pi times big R squared minus little r squared times dx. And that's the formula that I gave you on the previous page. Once we're to this point where we've drawn the region, we've drawn the strip, we've imagined rotating just the strip and drawn the little differential solid that we get from that, you need to come back to your graph over here and figure out what distances in this picture correspond with big R and what distances in this picture correspond with little r. Little r is like the radius of this little air gap inside here. So that's going to be the distance from the nearer end of the strip to the axis of rotation, which is exactly what I had you write down in that formula. So little r is right here. And big R is right here. Let's write down little r first. In terms of algebra, what is little r? It's the vertical distance from this point, which is on the graph y equals x squared, to this point, which is on the x-axis. So that's x squared minus 0, right? Because this point right here on the graph, this is x comma x squared. It's x comma y, where y is equal to x squared. And this point on the graph up here, just like in the previous problem, that's x comma y, where y is equal to x. That's just x comma x. So little r, this vertical distance is x squared minus 0. It's just x squared. And big R is x minus 0. It's the distance from the further end of the strip to the axis of rotation. It's just x. This sort of thing usually takes a little bit of practice, and what I find is that often I'll draw this region once, and then I'll need to draw it again much larger so I can get in there and label things and see what's going on. So a good habit to get in is just go ahead and draw this really big right from the start. Questions on why little r is x squared? So I'm thinking of all these points as being along the same vertical line whose x coordinate is x. And this point down here, of course, would be x comma 0 because he's on the x-axis. So each of these r's is a difference of y values because these distances are heights. The distance from the lower end of the strip to the axis of rotation is x squared minus 0 because the y value here is x squared and the y value here is 0. And the distance from the further end of the strip to the axis of rotation is x minus 0 because the y coordinate up here, the height is x, and the y coordinate down here is 0. So I plug these things in. Capital R was x, so r squared is x squared minus little r is x squared, so little r squared is x to the 4. And that's my formula for dV. Once you have your formula for dV, you just need to integrate it from the smallest x value in the region to the largest x value in the region. This point over here is 0, 0, and this point up here where x and x squared meet is 1, 1. So the smallest x value in my region is x equals 0, and the largest x value in my region is x equals 1. Or you can think of it as my strip will sweep through this region as x runs from 0 to 1. So my volume will be swept out as x runs from 0 to 1. And I integrate from 0 to 1 dv. Well, what's dv? So this is integral 0 to 1 pi times x squared minus x to the 4 dx. Now I can pop out the pi, and I'm left with the integral from 0 to 1 of x squared minus x to the 4 dx. The antiderivative step here is not challenging. This will be pi. Antiderivative for x squared is 1/3 x cubed minus an antiderivative for x to the 4 is 1/5 x to the 5. And this needs to be evaluated between the bounds 0 and 1. Again, at 0, we don't get anything. These are both 0, but at 1, we do get something. We'll get pi times 1/3 minus 1/5. And if you have a common denominator, this is 5/15 minus 3/15 is 2/15. So it's 2 pi over 15. So there's a lot of like spatial geometric reasoning that goes on in these. There's a lot of geometry. You need to be very good at drawing your graphs. You need to draw them nice and big so you can get in there and try to label all these distances, label all these points. Questions on this example? How are we doing for 9:19? Oop, we're just a little bit over. All right, so this is where we're going to end for today. If you need more time on last week's homework, please go into WebAssign and submit an extension request. I will respond to those today before I open up the new homework. So you'll be able to go in there and finish that up right away. There will be another homework opening up this week, right? Every week we're going to have a new homework. It'll always be due at the following Monday at the start of class. So please make sure you finish up homework 1 and please get started on homework 2 today. The homework this week is a challenging one. These geometry problems for most people are not super easy. So take your time and work hard, but make sure that you're not slacking off. So, you know, it's okay to work slowly, but you must be working all the time. Nicholas had a question, yeah. My advice would be to work, if you can work at the pace I'm working, that's plenty fast. I think I wouldn't rush ahead. I would work along with me as I go here. I think when I take little pauses and insert comments, that's generally meant to give you time to reflect and make sure that you're comfy with what you're writing so far. So I wouldn't suggest working ahead. Okay. All right, guys, then that's where I'm going to end the meeting for today. I do have an office hour this afternoon if you want to come by and talk problems. Remember, if you need more time on homework 1, please submit an extension request in WebAssign. There's no penalties for that. I'll be going in and clearing those out today, and I'll also be opening up homework 2, which is all this sort of volume stuff. On Wednesday, we're going to do a little bit more of this disk and washer stuff, and then on Friday, we are going to talk a lot about the method of cylindrical shells, which is a totally different way of looking at similar volume problems. I hope you guys have a lovely rest of your afternoon. And yeah, if you have any questions, come by office hours or shoot me a Canvas message. All right? Take care, guys.